All right, welcome back. Today we have two presentations. The topic is somewhat broad. It was deliberately designed so that we can cover it from different angles. The main theme is the suggestions engine for the people you may know. So imagine a social network such as LinkedIn, where you can like the posts, you can connect with people, you can browse the network, and sometimes you could add more people to your network. Obviously, at some point, the platform would like to have a special algorithm plus the UX feature to suggest people you may know so that the network grows. The backend for this is somewhat tricky, and today we are covering how can we approach solving that. Maxim, you want to start first?
Okay. Let's start.
I'm going to share my screen, and it's on you.
Okay, so I'm considering maybe a little bit narrowed task of searching for suggestion in a social graph. So basically, social graph is a graph. So we have nodes. Some nodes are people. Some nodes are, let's call them organizations or some features of people, and people have connections between these nodes. So, for example, like Alice has graduated school X and worked at some work W up to some time, and now she works at work Y, and Bob works at work Y, and they both, Alice and Bob, work in town Z. And for example, we know that Alice and Charlie, who has graduated the same school, are friends, and also we know that Charlie and Bob are friends, and we could predict maybe Alice and Bob are friends as well. So basically, we are solving the problem of adding missing connections, and we are suggesting these connections to, and then we are receiving. Maybe we will get Grab more connected after the suggestion is approved, or maybe the suggestion will be rejected.
Well,
we never know.
So you have a connector graph, and you have some predefined kinds of relationships, right?
Well, we can assume they are predefined. They are just. We assume that the type, the list, the count. There is like a finite number of types of relationships and types of nodes. For example, there is a node, the node person or the node school or whatever. Let's assume that we don't have. We don't. Well, basically, yes, and we have types of connections, like someone learned it in a school, or maybe someone teaches in that school. These are different types of connections, but both people are connected to the same node.
And this, based on this picture, all the relationships are many to many, I assume.
Yes, and we always assume that the relationships have some timing. So, for example, if two people lived in the same town, but they are apart from each other for about 10 years, it's not very likely that they met at any moment.
All right. Well, that's about the signals you would use. We'll get there.
So basically, the next slide describe this model a little bit more formally. Can you move to the next slide?
We are on the next slide, yes.
Okay. So the nodes like have a type, and maybe some other metadata that I omit for now. And as well, the edge, each edge has a type, time frame, and it could be, well, for optimization, some personal weight of this edge. So maybe someone cares more about his last employment place, but he doesn't want to remember the time when he worked in McDonald's. And okay, he has some communication with some people in the same McDonald's, but he doesn't want to talk to them. So an edge could have some personal weight that is trained. So basically, when a person approves connection to another person, that and they share the connection to that edge, this edge is trained positively, and when person disapproves, this edge trains negatively. Maybe I understand that this is a little bit maybe over engineering. Maybe we don't need it at all. We can assume that all the weights of the same. So the weights of edges are not are not like personalized. So okay, so what we actually want here.
I think an interesting question here is, these weights, are they part of some model output, or are they somewhat explicit in the way they are constructed?
Basically, I was thinking about having them as, it's not part of model output. It's more like a part of. So it's a feature of the edge. Because models, the model computation does not know. So it's more or less agnostic. It only knows about anonymized data, like the node types, edge types, maybe some. So
right.
Basically,
so for the actual model that would suggest friends or whatnot, this is the input. What I'm trying to ask is, do you think it can be the explicit input provided by the user or some experts, or is it an output of some other model? So, for example, as you said.
I agree. I understand. So basically, the user probably cannot provide this input. So it's more like maybe it's not a real weight. It could be just two numbers, like number of times we have suggested this edge as a clue for a friendship request, and number of times that it fits.
Right. In machine learning, there are differences between the strength and the intensity. But yeah, I think I get what you mean. All right, let's move on.
Okay, and basically our use cases are, well, first of all, when a new user arrives and fills some basic information, okay, he worked there, he learned, he visited that town, and so forth. Given just this information, we could start suggesting some people. Most likely, it's so unless it's unless this user gives some narrow enough information, maybe we will not suggest anything useful, but at least the user will be aware of this feature, that we will all the time suggest them some new friends.
Yeah, of course. So
also, the other this is the first. The other dynamic case is when the user just added some link. It could be a link to work or a link to another user. So the user added some link, and we can immediately request, does this new link provide some new suggestions? My
theory
is.
Hold on for a second. I think what you're talking about is suggestions based on some kind of a graph traversal, right? So it's as if you're constantly
It's
writing.
it's always suggestion based on graph traversal, but here is a little bit okay. Let's think about the last case is a suggestion based on observation of the whole graph. This is the most computation intensive, and on the other side, the batch, the most batch part of work. So we just can in background we can generate suggestions, and when the user comes to the site, we can show the suggestions we have generated. But this is the batch case.
What I'm trying to ask is, are we talking graph theory, or are we talking sparse matrix augmentation? I'll give an example. If you're constantly doing some kind of the minimum spanning tree construction, you would have, for example, job A, job B, or like school A and school B, and they have like their own cliques, right? People talk to each other, people work together. Then at some point, the lightning hits, and suddenly you realize that, hey, from certain school, people who work from here and from here, or people who work here and there, they actually know each other. From the graph theory perspective, if you think about it as connecting to these joint components, you would suddenly realize that all these people and all these people are potentially more connected. This is what I would imagine would happen if you talk purely graph theory. If you talk purely batch pre-computation, like matrix spectral analysis, this extra link, even though from the graph theory standpoint it can be like a million times stronger than the other one, would not have much value, because it just moves the cluster slightly closer to one another, but it doesn't necessarily make these people further apart than these people.
Okay, so in this sense, I'm looking at like local graph approach. I'm not trying to analyze the whole matrix. So each decision is made locally, so based on the neighborhood of these people, and each decision is made for people, not for for this big space.
Interesting. Well, so anybody from Facebook would immediately tell you that 5 or 6 steps from one person is the whole world. So locality is a vague concept.
Well, we don't. Basically, I don't think we need ever look at the whole. Need ever look at more than 2 hops.
Okay.
So if two users don't have anything explicitly in common, we are not suggesting them. So we are only. So that's the next slide. I'll talk about the computation model a little bit more. We are always consider that we are always consider users that have something in common, so they have some common connection. So this simplifies things a little. First of all, so basically, as I said. Okay, let's consider the one case, the simpler case, when then the user adds some node to the graph, adds some edge to the graph. So user A just added the graph, the edge to A to E. We are immediately. We are immediately sending a request. Who else is connected to E, and we are evaluating how for those who are also connected to E, we are evaluating how likely is it that A and B are connected. So how likely they are connected? We are looking at all their common connections, and using some model like all these links, given all these links, we are returning a number. Okay, the probability of being connected.
Well, not quite probability, right?
Well, in our model.
I think what you're doing here actually is a pure graph theory approach. What you're doing is you have the adjacency matrix, and you want to maintain its square. So whatever is reachable in 2 hops. And you provided some heuristics how to update this squared adjacency matrix if a new edge appears, which would almost always work just perfectly fine, especially, well, except the cases of huge nodes. But again, you're making a good point that if it's a huge node, like New York City, then it's not plausible to assume every single person in New York City knows everybody else in New York City. So you're kind of twisting this algorithm twisting the graph algorithm. You started from the graph algorithm and you're twisting it to suit your real life problem better. Am I making sense so far?
Yes, like that. So I basically square it. So square the graph and digest the graph, and basically this gives a list of candidates, and I can pre-trim the list of candidates to make the task more affordable. For example, I can ignore the huge nodes or have some other heuristics, and having this list of pairs. So now I have a list of pairs, and for each pair, I can compute some value. Let's say it's connection probability or whatever, and
you have to normalize it somehow, right?
Yes. What do you mean?
Well, you can't really come up with probability from the connectedness. You would apply some sigmoid function or whatnot.
Yes, absolutely. I will. My point for now is that so basically we have 2 models. One model is searching for candidates, and in the first iteration could be even more or less static, like such. We are assuming that everyone who has linked to these with 2 hops and the intermediate node is not very large, we can consider candidates. And the second step is for a candidate connection. We are basically for the candidate connection, the problem is relatively small. So we have the list of common common nodes in this type of these people, and probably we have something else. The nodes can be different, can have different types. You understand? So they could be like workplace node, or it could be a friend node. So if they have a common friend, this is another kind of connection, possible connection. So having this relatively small
what's
amount
interesting?
of data.
You know what's interesting? It's going to be small off topic, but I think it's interesting. I have not too long ago seen the same logic and the same graph applied to a totally different problem, to the power grid. When you're trying to build a microgrid, it's pretty much the same thing here. Even though I think in practice, microgrid would even be more graph theoretic compared to people you may know.
Yes, basically, I believe that the friend suggestion is more graph theoretic. If I was thinking about a different problem like movie suggestion, the graph theoretic approach would be probably not as plausible because the mapping between friends. So basically, it's just a different problem. My intuition says that for friend search, the the localized graph theoretic approach is more plausible.
In this case, if you want it to be purely graph theoretic approach, there is a trick you could use from route planning. So when you try to plan routes, you have to run the Dijkstra algorithm, right? When you need to drive from LA to Chicago. And Dijkstra is kind of slow, and the heuristic they use is called the highway dimension. So they run plenty of, without going into too much details, the claim is that if you're trying to go from point A to point B and they are far apart, they're going to share a lot of path with other routes from A to B, where A to B and far apart. You have to take highways pretty much. So you can just run two-way BFS from both start and end, and that's at the point they hit the highway, and at the point they are in the highway, you just know that the rest of the highway. So in your case, New York City or Apple are those highways. You can
no, it's not exactly. The highway approach makes sense here. I don't try to build the shortest path between A and B. I don't care about that.
Of course, yeah.
This is a different. So the highway approach is somewhat plausible here, and that's why I said about the personal weight of an edge. This is basically the highway question. So if they basically we could just use like the common edge. We know that an average person cares about the school that much, or that stuff. And this is like a model. This is like a global model parameters. On the other side, there could be personal preferences, and I'm trying to put like to have some knowledge about personal preferences encoded in the edge metadata. So basically, how often we have this user has used this edge.
I guess I'm jumping ahead of myself. I was just trying to optimize this. Once you connect to a big node, you want to optimize the computational capacity. Otherwise, most of the CPU would be used when people connect to huge nodes. But yeah, that's details.
Yes, you definitely don't want to run anything offline at anything online on huge nodes, and we should probably we should definitely limit capacity, limit the propagation mechanism, the propagation algorithm, to ensure that we don't get too many neighbors.
All right.
Okay.
And then after finding candidates, they are evaluated by common neighbors. So that's already the post-processing step, right? When you just
basically there are two. Basically, the algorithm is two-step. One is search for candidates, and the other evaluating candidates. Evaluating test of candidates.
Like most searchers do. Two-phase process: filter set and then final ranking. Yeah.
Basically, yes.
All right. Next slide, I guess.
Okay, next slide. Let's talk a little bit about the infrastructure.
That's plenty. Feel free to use your mouse pointer. It's going to help.
Okay, so basically, so we have some like relatively black box that is called prediction engine that was explained on the previous slide. And basically we have two kinds of requests. Live requests, which are expected to be limited, but which we want a relatively quick answer, and batch requests, which are as post filling the prediction cache. So we have so basically we have a request queue, which is just a queue.
Oh, I see.
And
these are the live requests.
Sorry?
On the left-hand side, you have live requests coming from the UI subsystem and batch requests coming from the batch controller, okay?
Yes. So UI, so UI subsystem. This is the citations like what I said, that when the user is at some link, we probably want a relatively quick reaction on that. Live request could have like low quality but but low latency. So basically,
in this design, what's the request and what's the response?
The request is, as I said, like find candidate for this user. The live request.
So in the case of
for this, so basically we have, if you go to slide 2, we have 5 candidates for this user given this new information, or just find all the candidates for this user.
All right. I'm back to the big.
So the live requests are usually find candidate for this user given this new information.
In terms of the product use case, the live requests would come every single time you're loading the page, which has these suggestions, right?
No, live request comes every single time when the user adds a new edge.
Oh, I see. So it's only to mutate the suggestions.
Yes, when the user mutates the graph, probably we can immediately give some suggestions.
Oh, all right. I thought I got it, and then I lost it again. So live requests are not requests for data. They're just requests to update the internal state.
Requests for predictions. So we have prediction engine, and there is another place which is called prediction cache. This is just a database. And this database collects the prediction that has been done. And when UI wants, when the user just logs in, the UI queries prediction cache. Is there anything interesting for that user?
So this part is queried first.
Yes. So when the user comes, yes.
This request, live request, if it's just a get request with no mutations, then it just goes straight to the cache.
Request is push request.
Right. So live requests.
It's always no. Sorry. Yes, I agree. The live request is like a new.
Right.
So
I think I understood you. Basically, whatever enters this request queue are not the get requests. They are the put requests or the post requests. They are the mutations.
Yes, they're mutations.
Right.
So basically,
and what is train here? The request to reframe the
train
model,
is maybe. This is just like I'll talk about that a bit later. So basically, I want to have some feedback to train to train the model, and
I don't like this suggestion.
Yes, maybe or maybe I like this. So when the user makes a decision, it goes to the engine, and engine basically dumps it to the training set. It doesn't do much. So maybe it should be, this line should be directly to the training set, but it seems to me it's cleaner when it goes through this prediction node. So basically, it's just feeding the training set.
All right.
And and also we have, if you look at batch controller, the batch controller is basically pre-filling the prediction cache. So when we have nothing to do, when it's night and we have too many spare CPUs, we are basically pre-filling the prediction cache for random users. They could be different. First of all, that could be different approaches how to select the users that we want to predict for. Maybe we want to visit like more active user more often, or doing some other magic. But in any case, batch request is just passing like sending information. Pre-fill this user, pre-fill that user, pre-fill this user. And to make sure that, and these batch requests are lower priority than live requests, obviously. And we have some load feedback to ensure that we don't overfill the engine or we don't overfill the queue.
So the batch controller is pretty much just a scheduler, right? It makes some. It's just a scheduler. It makes some guesses on.
Yes, it's a scheduler. Exactly. It's a scheduler that basically feeds batch requests.
So it needs to make some decisions on what are the most likely parts of the prediction cache to be updated, right?
Yes, it needs some. Yes, it needs some heuristic to understand which users are more interested to be updated.
Well, that's more like which users are more likely to be affected.
Yes, and here that's why I have
multiplied by how likely are they to see this.
Yes. So basically, how valuable are these predictions?
Impact prediction.
Mm-hmm.
Okay, interesting.
Okay, I'm not sure how it works yet. So basically, also the UI has, well, maybe it's a part of UI, but it has its own rejection cache. It's just to ensure that we don't spam the same user with the same prediction all the time.
Mm-hmm.
And
well, but won't this somehow happen organically? If the user sees the same prediction and doesn't react on that, that's a negative signal, right?
Yes, that's why I say rejection cache thing.
But won't the engine by itself catch it? So much like if I accept some suggestion, then probably it was interesting to me. If I don't accept some suggestion, it's also more input for the engine. Much like in search results, if you click on the third result, it's a signal the third result is good, but it's also a signal the first two are not good. What I'm trying to ask about, and again, I don't know the right answer, I'm just trying to ask random questions, is why is the rejection cache connected to the UI subsystem as opposed to the prediction engine?
Well, basically, UI will send this information as trained samples.
But do we really need this rejection cache? Can we just, when the user rejects someone, we can just update the social graph and add the node with like 0 weight, and it just organically won't happen again in predictions?
Yes, we can try to do it, but maybe the user just had bad mood today.
Well, but it's still a signal. Maybe every Thursday, this user is in a bad mood. Don't show anything.
Yes.
Yeah.
So basically, I don't think it's a good idea. So if the user just ignores someone without like explicit rejection, it doesn't mean that they don't know it, but we want to lower the priority and to avoid showing the same person again and again and again for some time. Maybe we'll return to this person in a month, and that at that time the user will be in a better mood.
Yep.
And we have some like signal that it's very likely that this user, we want this.
Small but important rephrasing. You add this edge not as 0 weight. You add the negative edge with high weight.
Oh, maybe. Okay.
Right.
And a little bit on the right is trainer, which only operates with the training set. The black box that only operates on the training set. And basically, it adjusts the parameters of the prediction model based on the trained set. And at some point, we can just flash out the new prediction parameter to the engine. Maybe do A/B testing to make sure that we didn't train something totally weird. And the new model will replace the old model. eventually.
When you say the model, I know your design is kind of agnostic to what kind of model is it, but I'm still curious. So what is the model exactly?
For example, the weights, the weights with which we are considering different kinds of connections. So for the evaluation part, it's pretty clear, for example, that we probably want to we probably want to value the connection through the company based on some parameters like company size or maybe something else, and also some company metadata, plus also but how exactly we are using these parameters. This is like a sea of different parameters we want to use for this model.
Interesting. Oh, so what's the order of magnitude of the number of parameters in this model? Because it's
I think not so many, like thousands.
Right. So you really are taking this hardcore fundamental computer science approach, graph theory and the statistically trained model. So, correct me if I'm wrong, but what I'm hearing is the following. You can have potentially a billion user network, but as long as you can have a billion user network and you can have another order of billion different entities. So of different relationships, different jobs, different cities, different schools or whatnot. Well, let's say a billion users and maybe 15 million other entities. What you're saying is that your model size would not change if you go from 1 billion user to 10 billion users. What the model size depends on is a number of different kinds of connections and stuff like that.
Exactly. I want a small model that only depends on the number of kinds of connections.
Right. I really like this approach because it has this property of explicability. You can reason about what does every single parameter mean. You can explain. You can argue that, hey, if you raise this weight by a tiny bit and you look at the diff, at a side by side of what has changed, it would make perfect sense. You would be able to explain every single change. Hey, I've raised the weight of company as a signal, and I've raised the weight of company Tesla as a signal. And suddenly you see that people who are connected through Tesla or in Tesla are more likely suggested to one another. I love this. It makes perfect sense.
Just one question. Does the model affect the weight changes that we get from users? So basically, you say you will just switch the model on the fly, but does the model itself affect those deltas and the change of weight or not? Or it's just like read-only for the weights?
Well, for the model doesn't affect the graph. So at least in my approach, the model, we are updating graph all the time the same way. And the model does not affect the graph itself. So we are training based on the samples that we have, and basically the model is like internal parameters of the prediction engines, and it has external parameters, the graph itself, or actually the subgraph we care about.
Oh, well, yes and no, because if I take one slide back, this edges would not be affected, but this evaluation by common neighbors is affected by the weights in the model, right? You would value some kinds of edges higher based on what the model suggests. If I'm getting this right.
Yes, based on the model, I will value some of these connections between some of the connection I value the different weights based on the model, and the model itself does not So it does not know about the graph much. It only knows about the training set.
All right, back to the diagram. What do we have left to cover here? We have the social graph database.
This is like a big box.
So what I'm confused about here is you have the prediction engine, this black square in the middle, and there is a reddish square behind it.
No, that's the same. This just many square.
Oh, so
many parallel instances.
So it's sharded.
Yes, it can be sharded as much as we want.
It just looks to me that if the batch controller is just a scheduler, then there are two distinct kinds of tasks to be performed by the prediction engine in this design. One is the real-time-ish answer. I mean, the live request from the UI subsystem would get to the queue, and you have to send a live reply within, well, I would say under a second. It's okay if this iframe takes a while to load after the whole page, but you have to respond pretty quickly. On the other hand, you have this background-ish update of your graph. So
that's why we need the priority queue.
The priority queue would help. Okay, so the priority queue would make sure that whatever has to be replied to instantly gets replied to instantly. But then, if I'm hearing you right, the vast majority of the CPU usage of the prediction engine shards would be spent not answering user queries, but recomputing the internal graph connectivity metrics, right?
Sorry, no,
so
let's
get back to the slide.
Yes, I suppose that most of the CPU will be used in batch. I agree.
Well, no, wait. This is not necessarily batch. It doesn't matter where this.
Batch means the recomputing. We have live requests and we have batch requests that are just recomputing the graph in background.
Yeah, I actually think I like the design, but I think you're constraining yourself too much, because if the batch controller sends the request about which specific key should the prediction cache update, then you can't do bulk updates. Effectively, in your design, the prediction cache is updated by pushing from the batch controller to the request queue. Update this user, update that user. Whereas if it's prediction engine centric, if the prediction engine itself is the origin of the update message, this engine could update tons of users at once. So going back to this slide, look, if you add the key.
Wait, let me explain. So my intuition says that even updating one user is expensive enough. So we don't really need to update user in bulk. Now, basically, updating one user means updating all the neighbors of this user. Basically, look at update the relations of this user with their neighbors. So it's in a sense it's bulk. So we are like.
So can the batch controller send a request such as update all the neighbors of user X?
That's exactly no. Okay. Update all the relations of user X.
Oh, I see. Okay.
So one batch request is update all the relations of user X.
So this makes a lot of sense to me. It just sounds like the prediction engine does two different jobs, and you may well split it into two parts. One is a live request, which may enter this or the other queue, and which pretty much bypasses the engine going straight to the prediction cache.
No. When we want to ask the prediction cache, we are just asking prediction cache.
So why would live requests end up in the request queue then? They could just talk to the prediction cache. Why would live requests?
Actually, all this. Wait. Actually, all the system works without a live request at all. Live request is an optimization case. So basically, if you don't have live requests at all, and only have batch requests, so what happens? Batch controller will update prediction cache for all the users in some pace, and when the UI wants prediction, it consults prediction cache. That's it. Now we probably want some optimization. For some user interaction, we want to get immediate predictions. That's the case like when the user adds some friend, we want probably to search for friends of that friend. That is what live requests are doing. So basically, the live requests are simpler and smaller than batch requests because they are only searching along one edge. So basically, when you have user A, we look at and we just know that user A and B became friends, and then now we look at all the friends of B and evaluate these users, the friends of B. Basically, the idea that live requests are basically are much smaller, and we want like a more real-time reply on that. The system will work without live requests, but like for like user experience, I think this the feature that we can immediately give suggestions after adding after the user mutate the social graph is probably high available, but that's just my theory. So that's why a bulk of the operations for live requests and batch requests are the same. So basically, the prediction, the inter-user computation is the same. A little bit different, like search for neighbors. It's just basically for live requests, the search for neighbors is limited to one edge, but that's it. So in general, it's the same. The requests are the same.
Right, that's what I figured as well. But then look, do I get it right that if you have enough capacity, if you can serve every single live request near real time, then since you only are considering one-hop connections, friends of friends, you would not need the batch controller at all.
We want symmetry.
So the live request.
Okay, so Alice has a connection to node X. Now Bob comes and adds connection to node X, but Alice is offline. When Alice comes online, we probably want to suggest Alice to Bob. Bob to Alice.
But wait. We do.
But maybe yes. Yes.
So wait. What you're saying is that the only way Alice would have Bob suggested is if between the time Bob connected to some shared entity and Alice joining the service, opening the service, the prediction cache was already updated for Alice because the batch controller scheduled that, right?
For now, yes. Maybe we want the symmetry update. That's I just added this symmetry update as an idea, and I don't know how much we want it. So basically, if Bob friends Alice, we want Alice to friend Bob.
It just sounds to me.
And maybe we want Subsystem to update some symmetry heuristics in prediction cache as well, but I don't know yet.
I just think this diagram you have the weights are misleading. In practice, the prediction engine is, I wouldn't say straightforward, but all it does is to apply the model. So it does the job, and then the magic, the secret sauce, is in your request queue, which is a priority queue. So it sounds like the combination, the interoperability between the request queue and the batch controller is where the secret sauce is. So imagine the request queue is a smart priority queue, where the live update that, hey, Bob is now connected to X, which also has Alice as a connection. Imagine your request queue is smart enough to parse this request that, hey, I'm adding the connection from Bob to X. And it automatically inserts with a lower priority, inserts also the message such as update all neighbors of X that will include Alice. In this case, your request queue begins incorporating some of the logic of the batch controller. It becomes the heaviest element of your stack. But now it makes a lot more sense logically to me. So effectively, if your live requests don't enter the queue right away, but if they go through this batch controller, which we rebrand as job scheduler, update scheduler, that's the same picture you're portraying with slightly, I think, less twisted explanation. Or what am I getting wrong?
Well, maybe it's just a different approach. So basically, I was probably thinking about like evolving model. Batch controller is to my mind, batch controller is something that we should start with, and maybe we don't need to update the users too often. So basically, the problem with this live then batch then live again is that probably you are basically probably you are trying to update the offline users in the wrong order. And I don't know if it actually matters.
I hear you. It's just, in my experience, again, it may well be my bias. I'm not saying that's the truth as it should be understood. In my experience, when you have two components, both of which smart, both of which apply their own logic, in your case, the request priority queue and the batch controller.
No, request priority queue is dumb. It's totally dumb.
So it's just
priority queue.
Standard priority queue, but then the question becomes,
that's static priority queue.
Okay, what's the priority?
Well, the number that we suggest, so it could be like live priority and batch priority. That's it.
Oh, so
probably don't need anything else.
Live priority has the highest priority, and batch priority is whatever batch controller assigns to it.
Maybe we don't need anything more elaborated than live and batch priority.
Okay, but in this case, if live priority is always higher than batch priority, then it's just two queues. One for live requests and one for...
yes, I agree.
Okay. In this case, somehow in my head, it makes the design simpler. You have the queue for live requests, and you have the batch controller, which also has a priority queue built into itself. And the prediction engine serves live requests first, and when it's idle, it can perform batch tasks.
Yes, that's that's okay.
All right. And then I think the last thing we didn't cover here is this symmetry update.
Well, symmetry update just basically the simple now mention that if A likes B, then probably you want to predict that B likes A.
Well, yeah, but it only matters for certain kinds of relationships. All right. Oh, okay, interesting. I think this works. So we get to
we just can update the prediction cache explicitly here.
Right. Yeah, this part is clear. Next slide, I guess.
Okay, next slide. Do we have anything? Okay.
Scale.
Discuss about the scale. I was thinking about like not very large to start designing for not like world scale system, but almost world scale system, like 100 million users.
100 million is not very large. It's huge.
It's very large. But like we don't think so. I'm just trying to and then trying to estimate what we actually want. And we think that each user has about 100 connections. This is, yes, there are some users will have much more, some have much less, but we know like in sociological or psychological capacity constant 150 people that a normal person may know.
Yeah, the Lemper number squared.
Yes. So it gives that basically it appears that the graph, just the connection graph, without any metadata is pretty small. So like kilobytes per user.
Yeah.
And basically it may so, and on the other side, if you get back to the prediction algorithm, the first part of searching candidates is basically traversal on this graph, and as the graph is small, we can just keep all of that cached in memory. Well, basically,
yeah, totally agree. I'm actually confused by people who think it's not a good idea to store the graph in memory. That's your most.
No, I mean that's cache in memory.
Yeah,
Do
of
not store.
Of course. I think that's not only the absolutely correct approach. I think it's the only correct approach. People who try to avoid storing the graph cache in memory are doing something wrong, honestly.
Mm-hmm. I don't know about the nodes, the node metadata that could be large enough. That then I'm talking about the metadata that we care.
Yeah, but
it could be large enough.
You can always shard it. As you said on one of the previous conversations, a simple least recently used cache for your key value lookup on metadata would take care of 99.9% of queries. So if you cannot store all the metadata in cache, you can store 2% of it, and it would cover 99% of requests.
I'm not sure. In this use case, I'm not sure. But anyway, it's easily sharded. The database is easily sharded because basically we just have a key value storage for each node, all the connections, and for each connection some metadata.
Mm-hmm. And then what's this one big prediction per user daily visit?
I mean, big prediction is like batch prediction. So I want to. So once again, I'm thinking big. So I assume that big request as it traverses all the radius neighborhoods,
right.
neighbors of the person. They could be big. Like it could be 10,000 nodes, maybe more than 10,000 nodes.
Yeah, if Elon Musk,
I don't want too many predictions, and that's why we can just if we update the batch predictions like once per day per user, once per active day user.
That does sound plausible to me. Yeah.
That's probably good enough. And if the user does not visit very often, we don't want to update the predictions daily. If the user doesn't care much, why should we care much?
Agree. Well, I mean, in this case, you can always trade CPU for accuracy.
Yes, we can always. So basically, when we feed the list of users to batch controller, we probably don't want to run every user. So we probably want to prioritize some users based on their activity.
Agree.
And based on cache staleness. So if for some user the cache is really stale, probably we don't want to update them often. But no, the cache is stale. We want to update them even if we haven't seen them. Maybe because probably we found some new data about this user.
Well, I mean, in my head, if we go back a slide hypothetically, in my head, this is a job of the bash controller. Even if the user is, even for the users who, let's say, log in like once a month or so, even for those users, you can prioritize who of them are more likely to have updates.
Yes, this is like maybe some box that was not the box beyond batch control that was not shown. So like the freshness manager.
Well, the batch controller is effectively a service by itself. It can have other components too. Yeah, here you get all the way to finding clusters, to spectral analysis, like collect the short list of the people who were likely more affected. All right. Any estimate on the number of machines?
So basically, it looks like the bottleneck might be internal traffic, might be.
Well, I don't quite see the internal traffic being the bottleneck. I mean, even if every single machine talks to every other machine, it won't grow these.
Well, if we are trying to hit database with petabytes, it might be not very good.
Even if you have to extract a petabyte per day, unless you do it on every pair of machines, on every single connection, this doesn't sound
maybe
like a lot.
Maybe it's not that bad. So basically, what else could be expensive is the prediction itself. So for a pair of nodes, and suppose we have like 100 of. So I hope this the evaluation of pair of nodes, given the whole information, should be relatively cheap.
Okay, let me rephrase
I don't know. My answer is I don't know.
Let me rephrase the question. So the model application is a black box. If it's super slow, then 99-something% of the time will be spent applying models. But let's discard that for now. Let's say somehow a model application costs you zero. In this case, what is the practical complexity of the graph database you would use? Since we're talking about pure computer science graph theory solution, it boils down to how do you shard the graph, right? So go in 2 slides back. How do you perform this operation?
So basically, the database could be just perfectly sharded. So let's like for each node, so we can fetch the. So all the time we want to fetch one of two things: either for the full information for a node, or connectivity of this node.
Well, the full information is not interesting. It's just a key value store.
Connectivity is not interesting as well. It's just a list of edges.
But then if you need to
but
then to look up those edges,
list of nodes. It's perfectly cached. It's perfectly sharded.
The list is sharded, but then you need to look up the list of edges of your neighbors. For which you
for each neighbor, for each person, for each node, we are storing the whole list of the whole list of edges.
Right.
It's not large.
Right, but then you're going to be making two
When
steps,
we
right?
Yes.
So for the second step, you need to look up the lists of all your neighbors, for which you would most often have to go to a different machine.
Yes.
Okay, so you would. I'm trying to understand what would be your biggest bottleneck in cross-machine connectivity. It sounds like most of the data you would be transmitting is, hey, node X, please tell me all the neighbors of user U.
From the network perspective, most very likely. Or maybe actually maybe not. Maybe most of the time it will be fetching metadata.
Metadata can be cached easily, and then the more machines you use, I'm assuming you're shared by users.
And
So
the graphs, it can be basically the list of nodes can be cached as well. So yes, you can. This is two-step approach, and if the no, I don't see what's wrong. I don't see what's the difference.
Me neither. It sounds to me that even with one level caching, you would do well. And if you cache the neighbors of neighbors, which you can also do.
You don't need to cache neighbors of neighbors. You just cache.
So if you only cache level 1, then every single task like this, you would ask all your neighbors to get back lists of neighbors of neighbors.
Yes.
So this, I don't quite see how would this not be the biggest offender.
We assume that, first of all, we assume that all the lists of neighbors are in memory.
That's true, yeah. Not talking about memory, only talking about network.
Network-wise, yes, network-wise. So for each request, so basically, you need to query each neighbor.
Although,
and for each neighbor, so that's why for each neighbor you just get the list.
I think I hear you.
That's small.
You're saying
it's small compared. After that, you have to for those neighbors of neighbors you have identified, you have to fetch metadata, which is bigger.
So how I think metadata
first step is linear. First step is linear of a number of connections. Second step is quadratic of number of connections.
Well, first step is quadratic when it comes to the network.
Fetching the subgraph is pretty fast.
Well, yeah.
What about parts of the nodes which are like New York City, where you have like huge list of?
We don't want the list of nodes of New York City ever. We have like a hard limit, like never return more than 1,000 nodes.
So we can just delete everything that has more than 1,000 users from our graph.
We don't need we don't use that. We don't use the nodes, the big nodes, for backpropagation. We still use them for evaluation. And for evaluation, these big nodes will be happily cached.
Or more like they just are bits in the bit mask. So
sorry.
So more like you would only have not too many nodes with, let's say, more than 10K out connections, and you so you have these many nodes of more than 10K connections. Let's say 10,000 nodes of 10K connections. For each user, you just have a bit mask of 10,000 bits, and these bit masks become feature vectors in your similarity computation.
Maybe. So basically, no. Basically, even if the details know the graph is sparse, you just need a list.
Okay. I think I see what you mean.
So basically, sorry.
I think
for evaluation purpose, yes.
I think what Maxim and I are trying to say is that you could have a lot more if you have to multiply million by million. And what you're saying is that you would never ever do it because there's a hard limit.
Yes.
This makes sense to me, although it always sounds a bit smelly. How do you define the hard limit?
Yes, hard limit is always smelly. I know. Maybe there is a better solution, but it's next. It's in the next iteration somewhere.
All right. Shall I go to? I assume there's one more slide.
Well, okay, we can discuss that. I just want to mention this. This is the last slide. Let's go.
Mm-hmm.
So basically, one thing that could be covered in the design, but I did not because I'm lazy, is privacy issues. So first of all, I want to. So first of all, we have like a hard requirement like GDPR. So if a user goes away, we want to ensure that the user went away. And there is no information stored. And on the other side, we want to ensure that the subsystems that don't care about user identity don't know about user identity. I don't know how much level of, so basically it's not totally easy to do because well, I don't know much about the user identity. Sorry, I don't know how much information can be extracted from the anonymized network, but actually a lot.
Well,
but we probably don't care for now.
I think you're solving level 2 problem. Level 1 problem here is what if the user wants to hide some past experience? So it is suggested offline before. Let's say I worked at McDonald's, and somehow it used to be part of the network, but now it's not. I would like to exercise my right to be forgotten, not about myself, but about this particular piece of data. Forget moral and data consistency issues. How can we make sure the design allows for that?
Fair enough. And here comes all the problem of caching here. So if you have got some information cached, then which is derived from something that is not, well, we are not allowed to use anymore. Then we could just clean up. We could think about cleaning up the cache, but it's extremely hard. Basically, we could just rely on cache TTL, cache validation. So basically, that's another reason why any prediction cache. So there are several reasons why any cache predictions could be invalidated after some period of time. So one reason is just because the graph is changing and something new comes. The other reason is our models are changing. Maybe with a new model we can give a different prediction. And this is another case when some parts of graph are mutated because of like privacy issues. We could mutate the caches correspondingly. So basically, maybe having just a relatively short cache lifetime is good enough.
On the one hand, it's nearly impossible to clean up everything. That's a well-known problem. But on the other hand, look, because your solution is such computer science clean, it's so graph theory centric. In theory, at least in theory, we could argue that your solution actually allows for somewhat proper cleanups.
Technically, yes. Technically, you can track together with the piece of information the way how you have received it.
Right. And
On the other side, well, okay, maybe you have something in common with this guy from McDonald's other than you work together in McDonald's.
well, that's the question of whether your system needs plausible deniability or
Yes.
All right. Well, I think this was a lot of fun. It actually made a lot of sense. Privacy aside, let's maybe some final words about this design. I think overall it's really good that clean computer science solutions can still exist. And I think people underestimate this kind of approaches. I'm almost positive that if you ask some modern hipsters whom you interview, hey, how would you do this? Every other one would say, oh, I just train a deep learning model. And I use all the features I have as signals, and let's hope something works out. And hey, this is my cost function. And look, it's improving, so I have a better model. And in a way, they would not be wrong. But it's really nice to know that you can solve these problems with no fanciness.
That looks too funny to me. I don't think this deep learning approach works on the model of that scale. So you need you still need some way to localize the problem. And then when you have localized, okay, you can feed this subgraph that you have for like local users to some model and get some results and think about that.
Well, yes and no. GPT-3, for example, would probably complete sentences differently based on whether John or Jane is from New York or from Apple. So I think the very assumption that the deep learning model cannot track this kind of context, this has already been challenged. Whether it can do it effectively is a different conversation. Whether it helps this kind of problem, again, we don't know yet. All right. So the interesting part is that I'm going to share my screen again. The interesting part is that I actually have another design.
Okay.
Which, ironically, we did not make any prior arrangements. How do I do this? I need to go here. Click on this guy. Oh, I need to go here. Now I remember. Thanks. We did not make any arrangements, but somehow I managed to talk about pretty much exactly what you did not cover and vice versa.
Oh, perfect.
So I'm going to assume we have this graph theory approach right away. I'm not going to go there. Instead, I'm going to focus on the real-timeness of the recommendations. So to me, real-time means that every single action is a signal, and whatever happened a second ago may affect the result of the output of the system a second later. Specifically, the trick is that I'm not trying to, basically, if the API call is give me my recommendations, here they are. I'm not trying to return all of them at once. I'm assuming I can reshuffle them later or even replace them later, because the interface, the UI, the UX only reveals them one at a time, or maybe the first few at a time. So if maybe it's different for desktop, mobile, and stuff like that, but maybe your screen could show like 2 or 3 recommendations. But then if you saw these 3, it's 2.5, for example, they will not change. But the next one may well change based on how long did it take you to scroll your feed. That's real-timeness to me. When I say every action or an action is a signal, so if you do something with any piece of content, it's a signal. If you don't do it, it's a signal. How long did you spend on the service until you closed the app or left the web page is a signal. And of course, how did you get to the service is a huge signal too, because you can open, let's say, LinkedIn voluntarily. You can open it from an email sent to you. You can open it this email can be from a friend, or can be an email from LinkedIn itself, that somebody has liked your post, for example, or somebody has subscribed to you, which is a different signal altogether. And then I covered that when it comes to subtle signals, even the mouse hover can be a signal. I hovered my mouse over some potential suggestion, or even I hovered my mouse over the like button. I didn't click like, but that's a signal. So to me, this problem breaks down into two parts, the infra part and the machine learning part. The infra part, I need to track these events, track them at real time, and ideally, I would like to store them all in a replayable fashion. I don't have to, but in a way, in order to retrain the model in what you call the batch mode, it's a lot easier to reconstruct everything from that replayable log, as opposed to just trying to collect everything from local sharded, like per shard caches. On the machine learning front, hey, that's exactly what I'm picking up on your slide 3 when you looked at the similarity metrics. So the similarity is, you can think of the dataset as a huge matrix, right? Let's say you have users as rows and content as columns. This is just users and content as in 2 dimensions. In your data model, you had more than 2 types of entities. So I would have 1 matrix per type of relationship. And then effectively the task is to, so this matrix could have like zeros and ones. 0 means no connection, 1 means there's a relationship. Of course, much like in your case, it could be different weights. It could be weights for 0, weights for 1s. It could be just a number from 0 to 1. It could be sigmoid or whatnot, probability, it doesn't matter. And what we're trying to do from the modeling perspective is train the model, or rather have the model that can predict the number in each cell. Or more accurately, we don't need all the numbers. We need to predict what are the, for a given row, what would be the top 3 or top 5 next columns with the possible largest numbers. The way you construct these distance metrics these days is usually via embeddings, which effectively would mean that unlike your model that has a small number of parameters, I would have a huge number of parameters. So I would fix some constant. It could be 8, could be 12, could be 50. I think 12 makes more sense, which would be the dimensionality of the feature vector per user or per piece of content. And then the way the embeddings are trained is that for a given user and a given piece of content, the dot product of these vectors is correlated with their level of interest in one another. If you just run PCA on this huge sparse matrix, first few singular vectors, single value decomposition, would give you what you need. In a way, vector number 0 would just give you static rank. So the most often followed users and the most often liked content, more or less. But then on feature vectors or on singular vectors, 2, 3, 4, etc., clusters would emerge. So you would have a cluster of, let's say, technologists, cluster of drug drivers, cluster of viral content, cluster of memes, cluster of whatnot. And then for each user, you would pretty much train, and this is all static so far. There's nothing dynamic. Once this embeddings model trains, what it does is it figures out what kind of interest structure does this user have in this clusters of interests. At the same time, for each interest, what clusters of users are more interested in this cluster. That's what embeddings are, and that's what the dot product does for them. So then, once you pre-compute this, approximately, you don't need it to be a precise solution. You can update it in real time. The way you do it is,
it looks like you are designing a dating site, not a site that detects that search for real world connections. You will combine the users, cluster the users with similar interests. That's nice, but this is a different question. Or maybe a different question from the searching of real world connections.
Right.
It's interesting as well. It's Probably this is even more interesting in the context of like LinkedIn-ish, when you want to find people that have similar interests to you.
Well, I think in practice,
But
you would combine our approaches. In practice, I would still suggest to use more parameters per model. I would introduce per user parameters, but also I would filter. I would filter suggestions. I would crop suggestions for the user, for most users, based on graph traversal, which you just implemented. And I would potentially have a bit, or rather a signal, that says, hey, this particular user kind of likes to be connected outside their immediate network, and vice versa. So to me, both approaches can be combined. And on the one hand, your approach provides filter lists to optimize computation. On the other one, it provides features. Because for many users, and you can find this cluster of users, they would just never ever go beyond their second connection. For other users, they would much rather connect with like-minded people, no matter how they are, assuming the static rank is high enough and assuming the interests are well aligned. So then mathematically, what I'm trying to say is that once you have these embeddings per users, you can shard by users. You can keep all the content, these feature vectors for all the content on all the shards. You can build some memory structures to look up quickly, more or less. Again, this idea of a small filter set. You have a million pieces of content to potentially recommend, a million other people to potentially recommend. You can quickly find the top 100 and then fairly compute top products there. And then what I would do is every single time I have a signal, every single time there's a new connection request, new swipe over or whatnot, I would change those embeddings, but I would change those incrementally by like adding small deltas there. And these deltas would be pre-trained by a different model. And the way I would train this different model is I would take a look at my batch. So let's take a small step back. I don't think I covered that. So I would have this PCA-ish embeddings retrained every once in a while. Let's say they retrained every 4 hours, or they retrained. Or let's say the training takes 6 hours, but I train them in parallel. So every 4 hours I have a new batch. Then I can take the lifetime of this 4 hours batch, and I can look at what happened between, let's say, between half an hour and 3.5 hours. So most of this range, except the beginning and the end. I could replay what happened there in batch for the previous batch, and I could train a model that tells me what were the best adjustments, what were the best deltas, the best coefficient. It's called learning rate. By how much should I have been changing those numbers in my metrics, in my embeddings, according to every single action, so that my prediction quality is high enough. If the learning rate is 0, I just have a static model every hour or so. If the learning rate is very high, I can overfit so that I could be tricked into something. So like some growth hackers could potentially find ways to exploit me. But clearly the right answer would be the right number would be somewhere slightly above 0. And you can find this slight margin. This would also be a model, which would also take into consideration other details about the user. So for some users, you'd be more aggressive. For some, you'd be more conservative. This can also be trained. And then again, last but not least, in my list, social features. Your friend X just did Y. That's exactly the reference to your own graph-based solution. And then I had to come up with a design, right? So the way it looks is pretty simple. I have the offline part on the left and real-time on the right. Everything is through the PubSub bus. The writers, whoever writes this bus in my picture so far, is at the right-hand side. So the PubSub goes right to left. In the real-time side, you have this per-user trackers. They keep track of some shard of the users and everything about the content or other users or whatnot, metadata. And they can talk everything, like each of them can talk to every other shard, but they throttle themselves. They don't send every single data anyway. They batch them into, let's say, 5 to 10 seconds intervals, and they only send the biggest deltas. So we can calibrate to not saturate the network. So basically, if some piece of content of some users gets viral, if some shard of users are now proving that certain content is viral, they would, within a couple of seconds, once this shard realizes this content goes up, within a few seconds, this data would go back would be sent out to the PubSub bus to every other shard. But this would not happen for every single piece of content, so that we don't blow our PubSub away. It's still reasonable. So then this PubSub is fed into all the way back to this embeddings trackers, to the sharded trackers, and that's where the users come in. Much like in your picture, the users don't come here. They don't come from the left. They come to the actual core system. But then the database, the offline database with batch training mode, is also subscribed to this PubSub. So every once in a while, it recooks its own data set, and it retrains two models, as I covered. One is this initial embeddings. I call it PCA because that's the term I often use, but these really are embeddings. And the other one is the model that suggests the coefficients by which those small numbers should be adjusted. And this is all pushed to some database accessible to these shards. Clearly, this is a NoSQL database, easy to shard. That's it.
Okay, so to understand some parts. One moment. So to understand correctly, this embedding tracker is pulling from database when it wants. So how exactly this connection works?
Yeah, I was thinking about this, and I deliberately left it unsaid. There are a few ideas. The easiest idea is that every single shard from here owns a portion of users, and this shard decides by itself when to switch to the new embeddings. It could do like a rolling update. So I have the users here, and I have a batch thread that updates them in some internal batches. Another idea is to actually, if we use this approach of consistent hashing, which I'm a huge fan of, you could actually design the system with some overhead. So each user will be owned by multiple shards. And you could randomize the results and then A/B test and pick the better approach, or you can average out the results. But the idea is that if you have multiple shards in a consistent hashed fashion, then you can pretty much reassign the new data coming from here, the new embeddings update. This guy could slowly begin penetrating the older shards that own this user away, and the new shards will be starting up that are based on the new model. This is slightly less predictable, but it also gives you more data for A/B testing, so that you could one idea why is it good. One reason I would advocate for such a solution is that it gives you immediate, cheap, almost free canary testing. If this is 100 machines and you have the new embeddings model, you add 3 machines, and you know that about 3% of your traffic goes through the new model, and you observe if there's any decay. And only if there is none, you slowly add more machines. Add doesn't convert. So you take one of the servers out of service, you restart it with a new model, it slowly catches up.
So the lifetime of this user tracker is when user is online. When the user goes away, you can scrap the tracker for this user, and then the user comes online, you are spawning a new tracker and pre-fetch it from database, correct?
I was thinking I always keep trackers on. I just have some least recently used cache there. So let's say I have 100 machines, and let's say there's no overlap. So each machine owns 1% of the users. How much of that is in memory, I don't care. Could be all of it. Could be 1/2 of it. Could be 1% of that. As long as this machine can reload its data from the database, it does the job. I don't think I'll have one tracker per user. I'll have one tracker per shard of users, which can afford to keep data about this user shard and the metadata of all.
I mean a logical tracker per user.
Well, logically, all I track about the user is the feature vector.
Sorry?
Logically, all I track about the user is the feature vector, their original embedding.
Mm-hmm.
It's a low-dimensional vector, but in practice, even a small number of dimensions does miracles. So if I know that if about each user I have a 12-dimensional vector of doubles, this pretty much encapsulates to which cohort, to which, loosely speaking, cluster of users does this user belong.
Yes, this is very good in classifying users. But when you get to the classification, so you know this, you have a billion of users and you have 100 of clusters, and it means that each cluster has 10 million users.
Hold on.
Do you
hold on? It's a good question, but it's not like this. If you have a 10-dimensional feature vector, 10-dimensional embedding, you don't have 10 clusters. You pretty much have 2 power 10 clusters.
You can you have 2 to the power 10 clusters. It's still just 1,000, not much.
But in practice, it's a long tail.
Clusters, sorry?
It's a long tail in practice.
The number of clusters is still much fewer than the number of users. And basically, yes, these users in these clusters have a lot in common. But now you have to trim this information to probably to match the actual users network. Maybe for some other criteria, you can just maybe sometimes the user is in a mood of discovering like new connections. Then this model definitely works, and this is a very good approach.
Well, that's why we have to combine our approaches, yours and mine. I think a better illustration for why a small dimensionality is enough would be solving a different problem. Let's say movies. On the one hand, there are tons of movie genres. On the other hand, it's not hard to reason that if you like those 5 movies and I like those 5 movies, we probably have common interests. So you could say that, hey, there certainly are more than 10 movie clusters. I would agree with you, there are thousands of them. But on the other hand, it's a long tail, it's an exponential distribution. So a small number of principal components, principal directions in your feature vector, in your embeddings, can tell the system a lot about your preferences. Same goes here with suggestions.
And now you get into the curse of a modern social network, which is bubbles.
Yep.
You are building bubbles like crazy, and you are not suggesting anyone out of the bubble, which is probably not which is probably good for business, but not very ethical.
No, wait. I see your point, but it's not valid here. It's not really bubbles. What we have is a bunch of. So if it's a multidimensional space, you have multiple arrows pointing in different directions. A cluster is a convex hull with a bunch of points here. You can have your own cluster of 5 people, and as soon as there's a new user who's pointing in the right direction, there's multidimensional space. You are the right suggestions for this user. I mean, I agree with you in spirit that the bubbles are a problem, but fundamentally, either you don't have static rank or page rank, or you have popularity penalty. That's always how it works. It's important to fight it, but it's impossible to fight it in such a straightforward way by paying these signals. You just have to work around them and have other diversity metrics and stuff.
Mm-hmm. Okay.
Can we get a little back to system design part? Where do we connect those your online thing and the graph from first design to limit, to filter the suggested users.
Oh,
How does it fit in the design?
I see. What you're asking is, where does this part, after finding candidates per Max's design, they are evaluated by common neighbors. This evaluation, in my book, implies there's a cost function that takes the input as the connectedness and outputs a number, how commonly related they are. In Max's book, this number is like a tuple, where the first element of this tuple is the number of steps you have to make. 1 is always better than 2. 2 is the highest you can go, and 3 you don't care. In my design, this is just one of the signals. And the overall strength of connection is a combination of multiple factors. One of them is a graph distance. The other one is embeddings similarity. Even on the graph distance, by the way, it's not just the number of hops. If Alice and Bob are 2 hops apart, but in case of Alice, she has 10,000 friends, and 9,000 of them are connected to Bob, it's 2 hops, but it's a really strong 2 hops. You need to capture that as well, both on the graph level and on the embeddings level.
I still don't quite understand. How is it in your system you find like if there are 3 users connected, A to B and B to C? How does it show in your data? It's like one of those tracked columns, or what is it exactly?
No, it doesn't. It doesn't. It's how I compute the similarity. So
you don't care about their real life connection, yeah?
I do. It's one of the signals. I have the ultimate model that measures connectedness. So let's say I have a request. And by the way, in Max's model, everything is cached. In my model, I have the optimized data structure to perform quick lookups. So the request comes in, and the request says, show me better suggestions for the user with this profile. The baseline of this profile for me is the feature vector. But there's metadata, and metadata is this user's ID and their connections. So then once I have a filter set, which in my book is based on their feature vector, of course I validate that as a second level ranking. And the second level ranking uses a lot more features that complement this dot product or can even override it. One of them is network similarity. And I agree that we have to use 2 filter sets, one based on embeddings and the other one based on graph similarity, and then apply the more expensive cost function to compute them. I still think it's a lot better to have a design where you can afford to compute this every single time per request, not just get a cached result. Because this enables this idea that if a new celebrity or a new viral post just emerged, in the 10 seconds during which I was just scrolling my feed, and I just click yes on some of the suggestions, the next suggestion that shows up right away may well incorporate this most recent post with no batches whatsoever. It would just be there because a second ago, the other machine, the other shard, has broadcast, hey, look at this content. It's super viral. Its static rank is high. Updated and it's embedded to this number. You will not be disappointed.
But isn't it a little different problem? It's you like not trying to find content that's popular. It's like how does it affect if 2 people know each other? They must both show that they like this exact content, and they'll pop up for each other.
Well, yes, it's a slightly different problem. I agree. It's more like I'm trying to combine 2 approaches. Well, yeah, Tinder could work here, by the way. If you read the OK Trends blog, they actually had this research done. I think a better analogy is still movie recommendations. I'm trying to suggest you movies based on the movies people whom you follow for recommendations liked recently. So if it's people you may know recommendations, then you absolutely must have them close to you in your social graph. If it's people you may be interested in following, well, if I just follow 3 Python deep learning people, I may well want to go to the conference or attend a conference if it's online. These days, everything online. I actually would appreciate a suggestion that, hey, look, this is happening tomorrow, and it's really related to everything you just indicated you're interested in. Deep learning, Python, and maybe some specific toolkit you're working on.
Okay.
Yeah, I think the truth is somewhere in the middle. It's essential to do both, I think. It's important to not forget the fundamentals, which is what Max covered. And as I prefer machine learning Asia infrastructure, I could not resist talking about the actual embeddings-based suggestions engine. All right. Shall we call it a day?
Okay.
Thanks, guys.
Thank you.
Take care.